Hello, everybody. Um, so this is gonna be a different video. I'm doing kind of a science video. Um, I don't care if you see my search history. All right, well, let's just get straight into it. I had to open a game in order to start recording because that's how my recorder works. Because I'm not screen recording, I'm recording through this app, which saves directly to my photos, so it's easier. But anyway, moving on. As you can see on my phone right now, we are talking about this new breakthrough in graphene quantum circuits, basically. Um, the reason I'm talking about this is because I actually have been getting closer to making sort of a working blueprint on like how we should start building quantum circuits so that they can both quantum entangle light sources and well, at the moment, I don't know if there's a way to use photons like electrons. So at the moment, there was a study done where another research paper. Like I've just been looking at all these online. Most of them are from like research centers. They're actual research centers. They have all their professors. They list all their stuff. So most of them are like I try and make sure that they're for the most part reliable sources. I'm like 90% sure on most of them. Like sometimes it just gives you the name, professor, university. You can check them up and then find them and like that's it. But you have like that's all the information you get. Unless you go to like the respective journals, but then you have to pay for stuff like that sometimes, and there's a lot more research that needs to be done into it. But the reason why I like talking about this stuff is one, it's pertaining to our future. I am 21 years old, so I'm probably going to be here when all the ice caps are melted, and hopefully we are not doing. Hopefully the environment isn't just completely destroyed. I know, very different. I'm like this gamer, YouTuber, and now I'm suddenly talking about science. I mean, I did talk about it once before, but that was like a short. I may release a few videos because this is very, very important. So, going back to the topic that I was talking about, using light and electrons in quantum circuits. So, there's this idea of what they call 2D materials, which is the graphene. So, they basically are forming, like, you can read all this if you want and pause the video. You do have to have, a little bit of knowledge in what they're talking about. But basically, I don't know if this is an accurate representation, but they found a way to make channels in like graphene sheets and like basically spots. So you can basically create these like highway streets um, on the um, sorry, graphene. I just had a brain fart. And you can also twist like angle some of the uh I guess graphene rings we call benzene. No, not ben. Well, carbon. Is that what it is? Here, give me 1 second. I just want to make sure I'm getting all these names right because in science, names matter. Wait, sorry, benzene ring. Oh no, benzene has hydrocarbons. Okay, yeah, that's the circle. Okay, no. So this is just carbons. But yeah, so they look like a little hexagon like this. They don't have the hydrogens, so just imagine all the hydrogens out, but they're all you know, not encoded, but they're all well, no, they're not all equipped. They're not all why am I forgetting these science terms? It's been a while since I did chemistry, guys. Not entangled. They're sharing their valence electron. Well, yeah, I guess you can call it the valence electrons. They're sharing their free electrons, let's say. Um, but if you twist a gate, or if you're missing some, like if it's not a full sheet of just pure hexagons and there's like spots missing, you get. I don't know exactly how the geometry would work because you would have to do all the math for all the electrons, but basically, it just everything kind of pairs up. And each carbon each carbon atom technically, excuse me, is supposed to have eight 8 carbons in total. I don't want to talk about chemistry too much. We'll go back to this, but first, um, what do I want to show you? Oh yes, so just real quick before I continue, because there's a lot of information to unpack, and I don't know if I'm going to be able to get it all through this video, but just so that it's 5 minutes in, so I should give you like what the rest of the video is going to be about. Basically, it's about using the circuits that they use in this research. So basically, just full graphene, because it's already we're already able to have a superconducting version of graphene in its 2D form, but it's hard to manufacture. It's dangerous, and it's a magic angle. I don't think they shared it, and I don't know. They didn't share. This was a while ago too. That they found out that you tune carbon to like a certain angle, and then it has insane 0% electrical resistance, which is good for any systems that you want to be quantum. Um, Not just specifically quantum, but more precise. And well, actually, no, we'll get into that precision part. It's a whole different type of precision. It's not more precise, but it's definitely way faster, and I guess you could say it's less. I mean, it's different because you don't have the electro resistance of like every material that you're using in a normal computer chip. Because the transistors are all made of semiconductors and conductors and insulators and resistors and just all these materials. And I don't think we have superconductors. Yeah, no, there's no room to. Yeah, no. There have been a lot of papers about room temperature, superconductors, but there have been a lot of skepticism going on, so we're not fully on that yet. Um, I was looking at graphene. What are they called? Pi bonds. Pi bond. Yeah. Okay. So here, because there's a specific hybridization. So this is a very weird way of visualizing it, because I'm pretty sure that's not how they look. Well, honestly, nobody knows how they look. But yes, actually, this is a great representation. So you have the so it's a weird to like picture this. So just imagine these are all like four balloons tied around. This is like how my chemistry teacher taught it to us, tied around an atom basically. Except it's in space, so the balloons are not going towards one direction. They're all pointing out equally from the center. Um, so those pi bonds are interesting to me because I think that is maybe a way to study um, how electrons behave as they travel through graphene. Because the problem with quantum computing, the biggest problem right now, like we're making a lot of advancements, but just, I mean, a little bit in precision, but like that'll continue to increase as we develop the technology anyway. So that's just a given for any technology. But we're also just learning how quantum tech works, how we're able to build it efficiently. Maybe sometimes I don't know how expensive the research. I'm pretty sure they're it's world research, so it's super expensive. But and they're working with like super small scale. Like this is all atomic. Like they can't even see it. They're just like on the screen or something. Like maybe the electron microscopes. I don't know. I haven't looked through one, so I don't know how those work. So I can't say from experience. But I just want to talk about the precision part because we have gotten down to like the 99% part, but we haven't gotten 100% able to calculate these like quantum pieces. And it gets more complicated as you quantum entangle electrons and photons, but it also kind of becomes sort of like a backup. So let me explain how that works. So, just imagine an electron is just carrying information like normal, like on a computer, like it's doing on my phone right now. Um, just travels through the wires, it goes in the direction that it needs to, and it sends wherever it needs to. Um, but it's a lot of electrons. It's like a stream rather than just a particle. What we're trying to do is get a single particle out of all the chaos that is happening. And there's a problem with that because there was another paper, actually a few, talking about quantum foam or the chaos in the void, how it's not really an empty void. Space isn't really an empty void. Um, Within a vacuum, like like I think it was B, like smaller than quarks and gluon, and they were thinking like string matter. There's like these little flares of like readings that they got that would just spontaneously exist and then go out, and they were particles basically that they were measuring in this experiment because they were trying to basically make a full vacuum, but they were measuring very precisely, which is good. Means that we now have a sensor that's able to precisely measure the vacuum. I was going to call it vacuum chaos or vacuum chaos coefficient. Still working terms on it, obviously, but this vacuum um, chaos coefficient is going to be very helpful for us because if it's a number that we can get, it might be easy to let's see, how do I say this? If it's a if it's a if it's a constant, I don't think it's a constant though because they say it's spontaneous and random. Well, it's chaotic. That's literally what the universe. It's a principle of the universe, a rule of the universe, the chaotic nature of the universe. But it's I don't think it's. I have to go and reread that paper, but I don't think they had like a constant value. So I think they just measured it. They didn't have like a certain value. I think we need to measure that and account for any of those particles, but this is like later. This is like once we have been able to build our quantum computers. And that's going to be like the part where we can fully utilize quantum computers. Because at that point, we'll just be in the improving phase. Because right now, we're in the improving research and a development stage. Mostly development, but there's still like it's like 3 bars on a bar graph, and they slowly change up and down. Um, Development's mostly constant, but it goes down later once you have like a kind of a finalized product. And with sorry, so I went a little bit off topic there, but with the like advancement of this technology, we can eventually be able to calculate um not just photons and electrons, which we can do now pretty easily, but quarks, which are harder. I don't know, like I don't know if we could get down to well, even if string theory is a thing, if there's like even smaller subatomic particle than the quark. Um, but yeah, they have down quark, up down quark. They have the 6 different types of quarks: top, bottom, charm, strange, up, and down. Each have or up, down, top have no, they all have half spins. Sorry, yeah, they have all have half spins. Um, and I want to talk about this spin part because we're moving on from the quantum void part because that's gonna be probably a next generation thing. I unless unless quantum computers advance really fast, like in the next 20 years, I'm probably not gonna have much to do with that. So I'll probably not talk about that at all. Um, but I did want to talk about using photons to basically change the spin of an electron, which has been done in a study, proven. I think 2 different studies. It's an accepted. It's accepted as an experiment, like it's a data result, but I don't think did they win a Nobel Prize. I don't think they won a Nobel Prize for that. Because most of these papers I read, it's just like, oh yeah, we found this out. Great, no Nobel Prize award or anything, but it's just like people like telling a newspaper, oh yeah, tell them this, this, and this, and give them extra juicy details. So I don't know how accurate. And then sometimes the writers may make the writing or the details a little bit more fancy or more attention grabbing, so that people are like clickbait. Um, I mean, it's a smart business model, but it still doesn't help the people who are trying to accurately get information on the internet. But yeah, why do I keep getting off topic? So yeah, we have to study first the way that electrons go through these new quantum processors, carbon quantum processors. Well, I guess graphene quantum processors. Um, Once we have an efficient way of studying how it moves through the different ways we can direct it and how you can build like little highways, basically just like doing Lego with that's like the easy way of saying it. Of course, this probably includes some very high laser precision. Yeah, there's like chemical process. There's some combustion, but don't you like press for graphene and you have to like really press, but also like break apart every single piece um that's on top because they come in layers, so you have to break them until there's a single layer. Um, and it's funny because you can produce graphene in its powder form, and basically between two tapes, between two pieces of tape. So you put on the sticky side, you put like a layer of powder, and then you basically put a piece of tape on top, and you keep doing that repeatedly, um, basically until you get every single layer off. But there's trillions, if not quadrillions of atoms. Actually, there's probably less because I don't know if graphene is super dense. It's not definitely not as dense as metals. So yeah, and it also has a lot of space between its pi bonds. But yeah, so pi and sigma bonds. Don't think the sigma bonds are super important. They actually I take that back. They're important for structure building in these graphene processors or these graphene quantum processors, because if you're able to um, well, actually no, let me explain it this way. Like I said before, you have to calculate every single electron and whether it's going to be bonded or not. I think, yeah, there's one per carbon atom. There's one, or there's a pair of pi bonds per carbon atom. So there's one on each side, and then it's connected to. But it's weird how this works because these pi bonds are like delocalized. It's more of a not a covalence. No, it's more polarized. Like the charge is polarized, which is why I don't know if most people know this, but why it's very good at conducting electricity, graphene, because the electron that you introduce into the system, basically a static, stable system, you can basically think of this graphene as a crystal, but it has a charge, and that charge is however many electrons it has in it. Technically, it's not charged, like the actual material doesn't have a charge to it, otherwise, it would be statically charged. Or you could dissolve it in water. Like there's like things that have charge. There's certain properties to those materials and elements um, that you can obviously see. The thing about carbon though is it just has these free pi bonds. So when you it's all stable basically, and when you introduce it's relatively. I'm not saying it's its base stableness, but basically it's stable where like it doesn't really matter. It's just gonna stay still. Of course, there's the whole you know rays from the sun and just rays and basically any type of particle that is traveling through our space time on Earth right now. Because if you don't know, yeah, there's literally I think quadrillions of particles literally just bouncing up all around um, inside the earth, through it, through us. Like most of them don't interact with us, but there's the occasional that do. Most of them are harmless. Some people get cancer. It's why you get skin cancer if you're out in the sun a lot, because you get exposed to the UV rays, which are they can penetrate your skin and penetrate your cells and hit, um, I don't know, some atom or something or some electron out of arrangement, and then causes a mutation stuff. Um, Super rare, but it does happen. And then there's, but that's more skin cancer. That's probably the fastest way to get skin cancer. Just sunbathe every day, especially in the worst weather when it's just like blaring hot. But yeah, these I keep getting off topic. I'm trying to, like, my brain keeps going into think mode where I'm saying stuff, but I'm thinking about other stuff, and I'm not thinking about what I'm saying. It just comes out. Um, but yeah, I just wanted to say that real quick. If you didn't know, pi bonds are the reason why um, electricity. Sorry, graphene can conduct electricity super well. Um, the last thing that I want to mention about this is the pi bonds. I did mention it before, so the sort of building mechanic, because there is the electrons you need to take into account. I don't know how bending. I mean, I guess you would remove, like, you can just remove a whole. I think you would have to remove a row of bending rings then, or you could just add rows. Um, but it's basically to keep the material as stable as possible, so you don't have to do like any introduction or any weird reactions. Because I don't know if it's possible to like have more electrons like in a graphene circuit or quantum processor. Sorry, because the way they showed it in that video was like very visceral. Like this is very visceral, vivid and visceral. Oh wait, sorry, that's the ad. Um, yeah, like if you think about our processes, if they're gonna look like this, what this looks like to me is gates and basically what you would call wires. I say this because I want there to be an easy way to deposit um, graphene onto silicon circuits so that we can incorporate those circuits on top of our existing circuits. Why do I say this? We need to start first. So, like, if we're going back to basics, so I won't continue for electron spin and using light to change that right now. I'm gonna more talk about the building block and the pi bond thing that I was talking about. But I'm getting further into the information, and it's a lot more information. So the reason why I said that we should put these type of circuits, so graphene quantum or processors, you call them, but circuits, whatever, on top. Well, I guess we could just say motherboard. So on top of another motherboard would be, and these are very different motherboards. Let me just make this really clear. It's a very minimal silicon board with very minimal transistors. Um, maybe like a plug for the wall so you can get some energy. Because you're not going to be delivering straight from your wall using lasers so that you can get light speed energy or whatever. You can probably have like a charging coil or some not transistors, not conductors, capacitors. Why do I always forget their name? Like if you just charge some capacitors and then use them. But yeah, you just need some way to integrate. Like I don't know how they set up these boards or whatever. Like maybe they just, yeah, actually I don't know. Maybe they just put this like in a gravity well and then shoot a laser at the individual electrons. But I don't know. I don't know if that's the best way of doing it. Another thing I do want to mention is that it's very different gluing or like adding these graphene layers onto other materials because they have their pi bonds, like I mentioned. So they do have those electrons, and they can react. They're not super reactive. I mean, it's a stable, relatively stable, mostly stable. Um, for the most part, it depends. I don't know how these little channels and gateways work because changing the angle would change where the electrons are positioned and so on and so forth. And you would just have a lot of different interactions. So the way I see this is like if and nor gates. So like you could think of like the left side as like the computer is sending information, and before it sends information to like the other half of the computer, it sends it through these three gates, and it's just for logic. So like, but I don't see the part though, because they need, so like those three gates are cool and everything. Like you look at those and you're like, wow, we're making so much effort. That's nothing. That's like if you wanted a yes or no statement or a one or a two. Like it's it would be a lot different. Another thing I do want to mention is that there's the whole quantum entanglement parts of quantum computers and quantum processors in general that is going to be very difficult because we're going to need a new, I don't want to say coding language because we can still relativistically relative I can't say that word, whatever, relative, I can't speak right now. So it would probably be easier to like just as humans because well the government doesn't give a shit, excuse my language, but it's true about any of this. They just recently started caring, and it's mostly because Biden became our president. And um I don't know, it just, what am I trying to say here? I'm just having brain farts over and over again. I feel like we're we're transitioning into a phase where quantum computing is going to take a big part of our lives, mostly because um, fusion reactors, fusion energy, clean renewable energy, those are reactions happening on a quantum level. You have the tritium and the deuterium basically fusing, and then you get the hydrogen and the extra neutron, or however the equation goes. But that is what we call quantum chemistry. So it's not, well, I don't know about we, but that's what I call it. I don't know the official name for it, but it's basically just using smaller particles than atoms. Because I know you use electrons and protons too in chemistry, but you using the bare minimum. They're mostly for, I mean, yeah, you use them everywhere, but you don't use like the more complicated stuff unless you're specifically doing things. And then when you get into the really complicated, like quantum physics, like chemistry doesn't teach you any of that except for light, because everybody understands C equals lambda V, right? But I think first what we're gonna have is these basically like this. So to wrap up this video, because I have to release the second part. Second part will be more about those electrons and their spin. This was more about me talking about just quantum circuits, quantum computing in general, and major problems. What I think is going to happen first, I think we need to do first, basically just everything that I wanted to get out of the way before I get into very specifics, because, well, I'm not sure about math, but like we're going to be talking some deep science stuff. So if you're not interested in that, then you probably shouldn't watch the rest of the series. But it does pertain to your future. So if you have some semblance of, knowing what's going to happen with all the energy that the future generations and you will be consuming, then hopefully you will watch this. I don't know if it will pertain to that, but I have a pretty good idea of how we can build these quantum circuits and quantum computers in general. quantum processors, transistors, capacitors, whatever, gates, logic gates, just like in general, quantum computers and circuits. But yeah, that's going to be it for this video. Thank you guys for watching AOG Gaming here. If you're enjoying the content, please like and subscribe. Really shows your support. Helps me out, keeps you up to date with our content. 58 subscribers and going strong last time I checked. So you guys are killing it. Keep going. You guys are amazing. Um, yeah, and I'm literally going to record the next video after this. So be ready for that one. And yeah, thank you guys for watching.